There is a machine that solves the problem. It exists. It has been tested. It works. Engineers at Johns Hopkins University Applied Physics Laboratory spent years building it specifically because the United States Navy kept running out of missiles with no way to reload them at sea. They called it TRAM, Transferable Reload at Sea Method. And what it does is elegant in its simplicity. Every previous attempt at reloading a VLS cell at sea failed for the same reason. Suspend a 3,500-pound canister from a crane cable on a moving ship, and physics turns it into a pendulum. The ship rolls. The canister swings. The clearance between the missile and the cell wall disappears. Steel meets steel. Game over. TRAM eliminates the pendulum entirely. Instead of hanging the canister from a cable, TRAM clamps it in rigid hydraulic jaws locked directly to a rail system bolted onto the VLS module structure. The ship moves, the rail moves, the canister moves with it, everything becomes one rigid body. The relative motion between the canister and the cell is physically eliminated because they share the same frame. The sequence works like this. A Lewis and Clark class dry cargo replenishment vessel, a ship like USNS Washington Chambers, pulls alongside the destroyer during a standard underway replenishment. The missile canister transfers across on an existing cable rig. Once aboard the destroyer, TRAM's hydraulic arms seize it. The rail system moves it horizontally into position directly above the target cell. The mechanism rotates the canister from horizontal to vertical, 90 degrees of controlled movement. An integrated cable and pulley system riding inside the rigid rail lowers it down into the cell. The entire operation runs on hydraulic power, not gravity, not momentum, not luck. July 15, 2024, first land-based test at the Naval Surface Warfare Center in Port Hueneme, California. Successful. October 11, 2024, TRAM goes to sea. Sailors aboard the cruiser USS Chosin CG-65 use the system to load an instrumented test canister into a Mark 41 VLS cell while underway off San Diego in Sea State 4. Real ocean, real movement. The canister went in clean. The Secretary of the Navy called it a game changer. July 2025, a second sea test aboard the destroyer USS Farragut DDG-99 during large-scale exercise. 2025 demonstrated faster reload rates, confirming the system could scale across the fleet. Full fielding was planned for late 2026 or early 2027. Then Operation Epic Fury began on February 28, 2026. TRAM was not there. Run the arithmetic slowly because the numbers are the story. An Arleigh Burke Flight the 3 destroyer carries 96 VLS cells at full combat load. At high operational tempo, launching Tomahawks against time-sensitive targets while simultaneously defending the carrier strike group with SM-6 interceptors, those cells do not last weeks. They last days. When the last cell fires, the ship has exactly two choices: stay on station with zero offensive capability and degraded air defense, or leave. It leaves. And here is where the bleeding begins. Transit to the nearest port with VLS loading infrastructure. Bahrain has the equipment, but during a high-intensity campaign, every pier is occupied, cranes running around the clock, ships queued in the harbor waiting their turn. If Bahrain is saturated, the next option is Diego Garcia, 12,500 nautical miles to the south. After that, Suda Bay in Crete, 3,400 nautical miles to the northwest. 1 week in transit out, 3 to 5 days under the crane, 1 week back. 3 weeks minimum during which a $2.5 billion warship contributes absolutely nothing to the fight. Now multiply that across the fleet. 10 destroyers on station. Combat tempo burns through their magazines in 5 to 7 days. At any given moment, a third of that force is in transit to reload. Another third is waiting at the pier. The remaining third is the only portion actually fighting. The United States Navy does not have a firepower problem. It has a presence problem, created entirely by its own firepower success. Before examining how the system broke down, it is worth being precise about what those 850 missiles actually accomplished. Because this is not a story about a weapon that failed. This is a story about a weapon that succeeded so completely, it outran the infrastructure built to sustain it. CENTCOM confirmed over 12,000 strike sorties against targets across the full depth of Iranian territory during Operation Epic Fury. Tomahawk struck IRGC command and control nodes. They destroyed ballistic missile storage facilities, the backbone of Iran's long-range threat architecture. They hit drone production lines and cratered military airfields. They dismantled naval bases across the Persian Gulf. Over 155 Iranian warships were destroyed or rendered inoperable, many at their berths, unable to sortie before the missiles arrived. The campaign's opening salvo on February 28 dismantled Iran's senior military leadership. Follow-on strikes set the nuclear program back by years. The President of the United States declared the core strategic objectives nearing completion within 5 weeks. 850 Tomahawks, $1.7 billion of precision ordnance. Every single one of them worked. But volume creates a problem that firepower alone cannot solve. Every missile that leaves a VLS cell is a cell that goes dark, and the only way to turn that cell back on is a concrete pier with a shore crane thousands of nautical miles from the fight. To understand why that pier is the only solution, you have to understand the physics that made every other solution fail. Start with the cell itself. The Mark 41 vertical launching system is the backbone of American surface warfare, installed on more than 60 warships, every Arleigh Burke destroyer, every Ticonderoga cruiser. Each cell is a steel tube roughly 25 inches square, just wide enough to accept a missile canister with inches of clearance on each side. Now think about what goes inside. A Tomahawk Block V cruise missile in its launch canister, 20 feet 6 inches long, 3,500 pounds, a turbofan engine, a warhead packed with several hundred pounds of high explosive, a solid rocket booster filled with propellant. This is not a forgiving piece of cargo. It is a precision instrument designed to be lowered vertically into a steel sleeve with surgical accuracy on a concrete pier with a shore-based crane locked to the ground while the earth holds perfectly still. Now try it at sea. A ship on the open ocean moves in 6 axes simultaneously. Pitch, the bow rises and falls. Roll, the hull tilts side to side. Heave, the entire ship lifts and drops on the swell. Yaw, sway, surge. Every second, the deck beneath your feet shifts in a direction the crane did not anticipate. Suspend a 3,500-pound canister from a crane cable in those conditions, and the canister becomes a pendulum. The ship rolls left, the cable swings right, the ship heaves upward, the canister drops. The correction lag between the ship's motion and the canister's inertia creates an uncontrolled oscillation. At sea state 3, moderate swells, nothing exceptional. The amplitude of that pendulum swing exceeds the clearance tolerance of the VLS cell. The canister strikes the cell wall at an angle. Steel meets steel. Inside that canister, rocket propellant and a warhead. One wrong impact and the crew is not reloading. The crew is evacuating. The math does not negotiate. The Navy tried to solve it. Early Arleigh Burke destroyers, Flight Y and Flight 2, DDG-51 through DDG-78, carried a partial answer. 2 strike-down modules, one forward and one aft, each housing a small crane designed to lower canisters into VLS cells. Each module consumed the space of 3 missile cells, reducing total capacity from 96 to 90. But there was a second problem the pendulum alone did not explain. Those cranes were rated for shorter, lighter canisters, not the full-weight Tomahawk that would come to define 21st-century naval strike. Even on calm days, they could not reliably handle the one weapon that mattered most. And calm seas in the Arabian Sea or the Western Pacific is a condition that exists on a planning calendar, not on an ocean. After years of testing, the Navy made a decision. Starting with Flight 2A, DDG-79 onward, both strike-down cranes were removed entirely. In their place, 6 additional VLS cells. Total capacity rose from 90 to 96. 6 more missiles. And in exchange, the United States Navy permanently surrendered its ability to reload its primary weapon system at sea. That trade made sense in 1999. The assumption was straightforward. Wars would be short, strikes would be surgical, and 96 missiles would be more than sufficient before any ship needed to return to port. For 25 years, that logic held. Then came epic fury. This gap between missiles fired and missiles available is not a new phenomenon. History has been signaling this problem for years to anyone paying attention. In the Red Sea in 2024, destroyers defending commercial shipping lanes against Houthi drones and ballistic missiles burned through their SM-2 and SM-6 interceptor inventories within weeks. With no ability to reload at sea, those ships withdrew to Mediterranean ports, Ceuta Bay, Sigonella, Rota, leaving gaps in the defensive screen that took days to fill. The Houthis noticed. They attacked during those gaps. In May, the tanker Wind received a ballistic missile strike that destroyed her propulsion. In June, the bulk carrier Tudor was hit and sank. The cargo ship Verbena was struck days later. 3 ships damaged or destroyed in the windows between one destroyer leaving and the next one arriving. Go further back. February 23, 1945. The ammunition ship USS Shasta pulled alongside the carrier USS Bennington in the open Pacific and transferred bombs using a cable rig, the Burton transfer method. Winches, booms, cargo nets. Crude, dangerous, effective. Sailors manually handled ordnance between 2 ships steaming side by side at 12 knots. It worked because a 500-pound bomb is a steel sphere. You can roll it, cradle it, absorb the impact. It tolerates rough handling. A Tomahawk canister is not a steel sphere. It is a 20-foot precision instrument containing volatile propellant and a focused warhead. There is no cargo net that solves that equation. There is no Burton rig that threads a 3,500-pound needle through a 25-inch opening on a moving deck. For 80 years, the Navy has transferred fuel, food, and conventional ammunition at sea without issue. The one piece of cargo too precise, too dangerous, and too dimensionally exacting to transfer at sea is the missile that defines its entire combat power. Tram was not a surprise. The Navy knew this moment was coming. The Red Sea had already demonstrated it. The logistics modeling had already shown it. The development timeline was deliberate, funded, and progressing. 2 successful sea trials. Fleet fielding scheduled for late 2026 or early 2027. By every measure, the program was on track. Operation Epic Fury began February 28, 2026. The fleet fired 850 Tomahawks in 5 weeks with no ability to reload a single one at sea. Tram, the machine that eliminates the pendulum, the machine that ends the 3-week bleeding loop, the machine the Navy spent years and significant investment developing specifically for this scenario, sat in a development pipeline while destroyers turned south toward Diego Garcia one by one. The solution existed. It was proven. It was not there. It arrived one war too late. But here is where the picture shifts completely. Even if Tram had been fielded on every destroyer in the fleet on February 27, 2026, the day before Epic Fury began, the magazines would still have run dry. Because Tram moves missiles. It does not build them. Raytheon, now RTX, currently produces Tomahawk cruise missiles at a rate of 60 to 90 per year, a sustainment rate calibrated for peacetime budgets and peacetime assumptions. 850 missiles fired in 5 weeks, 60 to 90 produced per year. The fleet consumed roughly 10 years of production output in 35 days. The defense industrial base is responding. Raytheon signed framework agreements in February 2026 to scale production toward 1,000 missiles per year. But each Tomahawk requires more than 100 subcontractors, thousands of precision components, and a production lead time of 18 to 24 months from order to delivery. Scaling a factory is not a software update. It is metal tooling, supply chain restructuring, and human hands trained on processes that cannot be rushed. Go back to the decision made in 1999. Remove the cranes, gain 6 cells. At the beginning of this analysis, that trade looked like the mistake that created the problem. At the end, the picture is different. Even with the cranes intact, even with Tram fully fielded across the fleet, the magazines would still be empty, because the constraint is not physics, it is not distance, it is time. The time it takes to forge metal, assemble guidance systems, test propulsion, and deliver a finished weapon to a ship that fires them faster than any production line on Earth can build them. TRAM solves the first equation, how to move a missile from a supply ship into a VLS cell at sea. It does not solve the second, how to ensure there are enough missiles on that supply ship to begin with. Epic Fury is the first conflict since World War II in which the United States Navy consumed precision munitions faster than its industrial base could replace them. That is not a weakness in the traditional sense. It is a new category of strategic problem, one that any force powerful enough to sustain high-intensity combat operations for weeks will eventually face. Go back to the image that started all of this. Somewhere in the Arabian Sea, 200 hours, a $2.5 billion destroyer swings its bow away from the Iranian coastline and heads south, not because it took damage, not because the crew needs rest, because 12 hours ago, this ship fired its last Tomahawk cruise missile, cell number 96, into an IRGC command node buried inside the Zagros Mountains. The missile worked. The target is rubble. The ship is intact. The crew is ready, but the ship is leaving. 96 vertical launch cells, every one of them empty, 20 feet 6 inches long, 3,500 pounds each, $2 million per missile. And this ship has no mechanism to put a single new one back inside those cells. Not out here, not on the open ocean. The only place this destroyer can reload is a concrete pier with a shore-based crane. The nearest one capable of handling the load is over 2,000 nautical miles south at Diego Garcia. 1 week to get there, 3 to 5 days under the crane, 1 week to return, 3 weeks out of the fight. A ship built to dominate the electromagnetic spectrum, carrying the most advanced integrated combat system ever installed on a surface combatant. Sidelined not by enemy fire, not by mechanical failure, not by a decision made in this war, but by an empty magazine and the absence of a machine that can fill it. That machine exists. It was tested. It works. But it arrived one war too late. 850 Tomahawks fired, $1.7 billion of precision ordnance expended in 5 weeks, the highest expenditure of a single precision weapon system in any conflict since the invention of the guided missile. More than the entire 2003 Iraq campaign. And when the last cell went dark, the most powerful surface combatant ever built turned south and sailed away from the fight it was designed to win. TRAM will fix part of this. A hydraulic rail bolted to a VLS module, rigid jaws clamping a 3,500-pound canister, the pendulum eliminated, destroyers reloading alongside supply ships 30 nautical miles behind the battle line instead of steaming 3 weeks to a concrete pier, presence gaps closing, the bleeding loop ending. When TRAM fields across the fleet, it will fundamentally change the logistics of naval combat. But TRAM moves missiles. It does not manufacture them. It takes 18 months to produce a single Tomahawk cruise missile. It takes 12 seconds to fire one. The machine that decides the outcome of modern naval warfare is not the radar that finds the target. It is not the missile that strikes it. It is not the VLS cell that launches it or the hydraulic rail that reloads it. It is the machine on the factory floor, the one that turns raw metal, precision components, and 18 months of manufacturing labor into a guided weapon. That machine does not answer to fleet commanders. It does not accelerate because an admiral needs more missiles by Thursday. It answers to physics, the physics of metal, heat, and time. And in any conflict intense enough to matter, that machine is the one that decides who wins. At Navy Equation, that is the equation we track, because the weapon that flies is only as decisive as the factory that built it.